Well, like everyone else, I want to thank the organizers for inviting me here and for their hard work in putting together this wonderful conference. So I'll try to explain some ideas, and hopefully we'll have fun with renormalization. So let's see if this works. Can you guess what this is? Feel free to shout from your seat. Have you seen this before? Anyone? No one has seen these pictures? RG flows, yeah. Anyway, this picture is taken from textbook where it describes one of the models in population biology. So this is a famous model which describes two species that compete for the same food source. For this reason, the model is often called sheep and rabbit model. And here the X and Y are, I guess, these two populations. There are quite a few parameters in the model, R, K, K prime, and so on, which reflect the source supply. So in this models, there are different interesting fixed points, I guess. One of them is where one species dies, the other is where another species dies. There are two other fixed points. And as you vary parameters, such as food supply and so on, the system undergoes a change, which is called transcritical bifurcation, and there are two different regimes of the system. When I saw this picture, it literally reminded me of this picture taken from a famous paper where these guys went on enormous quest to compute 5-loop renormalization beta function in the ON model, and there are many similar systems, of course. So here you also see different regimes and same disposition of 4 fixed points and their relation. So what I want to do in this talk, I want to entertain a new idea and consider a new connection between two different subjects. Always new connections are fun and exciting. Steve Jobs called it connecting the dots. It's like playing with a new toy. You want to see what it gives you. You want to see what it can do for you. Well, of course, until it breaks. But it's also a dangerous endeavor in the sense that it will lead to new connections and new predictions. And if you're trying to explore this new direction, there is no safety net. There is no other path to follow. And whatever these new predictions or connections are, you have to commit to them. So, and that's the danger, of course. So as you can probably guess, the connection I'll try to explore is the connection between dynamical systems and renormalization. So in dynamical systems, a space with a vector field is called, well, a dynamical system. So therefore, if you think about space of couplings, sometimes called theory space, this is really a dynamical system if you think about beta function as a vector field that drives the flow. Then the dictionary goes pretty well. For example, in dynamical systems, one of the main questions is, what are the critical points where the system settles? And for us, these are precisely conformal fixed points of the RG flow. So this is a nice analogy. And imagine yourself sitting in a living room and reading a textbook where you could see these pictures. So natural question is, if we continue reading this textbook, are we going to learn anything interesting, anything new that we haven't seen before? So one question, for example, could be, if I put myself in the frame of mind of dynamical system person, can I learn anything new about stability of conformal fixed points of the flow? This is kind of a local question, just about fixed points. More global questions could be, are there any new topological invariants that these people use and whose names have not shown up in string theory literature or field theory literature? Is there any new topological information that we could possibly use for our purpose? And perhaps in a different vein, what about different processes that control mergers and disappearance or appearance of conformal fixed points, which often have to do with strongly coupled phenomena? So this will be kind of questions that probably you and I or anyone else who sees this pictures next to each other would naturally ask. And it turns out that the answers to these questions is yes, yes, and yes. So there are actually new topological invariants that these people considered that go by names that we have never seen before. So this is new opportunity. Classification of fixed points and different types of behavior in the system governed by algebraic equations which are very similar to singularity theory that we use on Calabi-Yaus to study field theories and geometrically engineer interesting physics in lower dimensions. And the element that I'm going to use in this talk is question about merging of various fixed points, which also will have interesting implications and some similarities to physics that we have seen. So the element that I'll focus on, again, there are many tools, and I'll try to avoid what's called curse of knowledge and bombarding with too much. So I'll try to focus on the smallest possible ingredient which is useful and makes new predictions. And the element will have to do with a branch of dynamical systems called bifurcation theory. So roughly speaking, again, very roughly, this is a fancy name for theory of phase transitions. But it has its own tools, and we'll try to apply these tools in our context and see if it gives anything new, anything concrete. Where I want to apply these tools is context where other tools hesitate. As Nati beautifully summarized for us yesterday, the kind of techniques we have where we can control renormalization group flow away from the fixed points are usually supersymmetry or some type of perturbative expansion, such as 1 over n expansion or the usual old-fashioned Feynman diagrams. So the philosophy I want to keep in mind and use is where we keep things that work, and usually that means keeping control, very good control of our G-flow renormalization in the vicinity of the critical point. We can actually compute a lot, and for example, Igor in his morning talk presented us with beautiful illustrations of that. But we usually, unless we have supersymmetry, we don't know much about renormalization in a strongly coupled regime, far from the fixed points. And that's precisely where I hope this can provide us with an opportunity to say something. That's exactly where we would like to learn something new from topological or perhaps other techniques that these people can teach us. Of course, you can also ask various fun questions. If you love dynamical systems, you could ask, can I find a strange attractor as our G-flow in some system? But I'll try to be more practical. My goal is to learn about renormalization using these techniques and use their tools for our purposes. Of course, one day, one might hope that this will lead to a new way of thinking about renormalization in strongly coupled regimes. But again, for today, this is just going to be a tool similar to the tool of 1 over n expansion and other techniques. So this is just a machinery. There are many examples where you could try to play with this new toy and apply it. Among non-supersymmetric theories, these are most prominent examples which first come to mind, such as three-dimensional ON model, three-dimensional QED, four-dimensional QCD. And as you can imagine, four-dimensional QCD will actually turn out to be the most interesting system, not only because it's closer to real world or our heart as string theorists or particle physicists, but it actually exhibits at a very technical level much more interesting phenomena or ramifications of the phenomena I'll try to tell you about today. Today I'm going to focus on three-dimensional QED. This is just for concreteness and for simplicity. Again, I want to illustrate one particular simple point, the simplest possible point, so I can convey the idea. And you can probably imagine how to go to more interesting examples. I have no personal attachment to three-dimensional QED. So if you have your favorite renormalization process that you want to understand, the strong coupling one, you can approach this talk with a viewpoint of, OK, what could it do for me? What would happen if I apply these techniques to my flow? So I'm going to focus on three-dimensional QED, and the concrete prediction which will come out of it following this bifurcation analysis is going to be a prediction for conformal dimension of an operator that will go as a square root of number of flavors. That's a very concrete prediction. And good thing about any of the systems which I mentioned is that this prediction can be verified. So first of all, it can be verified by lattice calculations, which are pretty good for QED as well as four-dimensional QCD. So sooner or later, technology will be good enough where this will be either right or wrong. And of course, I hope it's right. So secondly, three-dimensional QED is related to number of condensed Murray systems. So I went on a quest to talk to my condensed Murray colleagues and try to learn whether this can be immediately confirmed or ruled out if we take information from existent systems which have some contact with three-dimensional QED. I'll be talking about three-dimensional QED in a conformal window, and these are scaling dimensions of these operators in a conformal window as we approach critical number of flavors. And somehow most of the studies, theoretical as well as lattice, are focused not so much on the behavior of this scaling dimension with n, but rather on finding the critical value of the number of flavors. And unfortunately, that's the difficulty for checking right now whether this is correct or wrong. So the upshot is that I don't know yet. But again, good thing is that this is something that can be verified in the real world, and we can see it either in the lab or in a lattice, and we'll know soon. So in fact, some of the theoretical studies of this model do not immediately ask for behavior of this conformal dimension. Some of them do, but not too often, and it's not very difficult to extract this. So in fact, this conclusion, which will follow from the analysis I'm going to present to you, actually goes against some of the recent or current existing proposals in this stage. So what is the theory? Theory is three-dimensional quantum electrodynamics, so it has a gauge kinetic term and a fermion kinetic term. I'm using the formalism where my fermions are four-component Dirac spinors. In the literature, they usually number of flavors in F denotes either number of two-component or four-component spinors. I'm using notations where we're talking about four-component Dirac spinors. When number of flavors is very large, then the screening due to fermion fluctuations keeps the coupling constant small, so we're remaining in the disordered massless phase, and the theory has a fixed point, infrared fixed point. And as number of flavors become smaller and smaller, then a coupling gets stronger and stronger, and at some point it is believed, or there is some evidence, that there is a transition into phase where spontaneous chiral symmetry breaking takes place, breaking this chiral flavor symmetry to the smaller group. Here in three dimensions, if we're talking about four-component Dirac spinors, just like in four-dimensional case, then apart from gamma 5, there is also gamma 3 matrix, which plays the role of gamma 5. So each fermion flavor in this formalism comes with U2 symmetry, so that's why we have U2 in F in the first place. So the question which is often asked is, what exactly happens at this point, and where exactly this point is? So this, in fact, is probably one of the most asked questions in the subject. What is exactly the value of NF critical? Well, before I go to that, I want to point out, just like I mentioned before, that when I was trying to learn about possible experimental realizations or whether there is any evidence or information about behavior of scaling dimension with number of flavors that this analysis predicts, I didn't find that, but along the way I found lots of applications in condensed Murray systems. So we're talking about 2+1 dimensional theory, and it actually appears quite often in many contexts. First of all, any layered condensed Murray system or any surface of bulk sample will necessarily be 2+1 dimensional, so dimensionality is obvious. Moreover, in three dimensions it often happens, in fact you can show that in many systems it's a generic phenomenon, where a valence band touches the conductance band, and if this happens, then dispersion relation for effective quasi-particles is precisely the Dirac dispersion relation. So we basically get Dirac fermions. The typical system where this was considered in many incarnations, in fact, this application changed over years, and there are quite a few different applications of QED to high TC Cooper superconductors, is where you have D-wave superconductors. They have 4 nodal points on the Fermi surface, and each nodal point contributes 2 components of fermions. So total we have 8, and if I'm counting 4-component fermions, that means that this system is NF equals 2 in my notation. So there are many other interesting applications to layered systems such as graphene or surface states and so on, but I hope I explained for you the basic principle how it comes about. So The critical value, this NF critical, is really hard to capture. Basically, if you think of a number from 1 to 10, there is a good chance you'll find this number within 10% accuracy on this list of various predictions and estimates. And many of them come from lattice simulations. Many of them come from functional RG, epsilon expansion, F theorems. In fact, some of these references, which I put next to here, are by people who are here in the audience. Again, good thing is sooner or later we'll know what the answer is, simply because this is something that can be easily put on a lattice. And again, there are many undergoing lattice studies of the system, lattice simulations, and hopefully one day they'll do the job. So today I'm going to focus on, I'll just take two random RG flows predicted by some of these works. One is based on one loop epsilon expansion, the other is based on perturbative RG in the large N limit, which is quite natural. These are both theoretical studies, and I'm going to examine this through the looking glass of this bifurcation theory to see if it leads to anything new. And I already told you a result. I told you already what it leads to, this characteristic square root behavior. So if I run out of time, I don't have to worry because I told you the main prediction. Okay, oops. This is very interesting. That was too fast. Sorry for the glitch. Okay, so these are the two studies. And they both analyze system perturbatively. Again, one does it at large N number of flavors. The other analyzes the system starting with 4 dimensions and performing epsilon expansion, very similar to what you've seen in Igor's talk this morning. And both of them, although in a rather different form, predict how a scaling dimension of 4 fermion operator, this fermion quadrilinear, behaves with a number of flavors. So this is NF, and this is the plot. It starts life as irrelevant operator for a large number of flavors where semi-classical or weak coupling approximation is valid. And at some point, as you decrease NF, it goes through marginality and then suddenly becomes relevant, which is how people believe the onset of chiral symmetry breaking may happen if this scenario plays off. So these studies lead to somewhat different values of NF critical. One of them gives a 6, the other gives a 2. Again, they both try to make an estimate of error of the accuracy of this prediction, but they're quite well off. And in the table before I showed you that this is, we're all over the map here. But I want to point out that this gentleman actually did something nice. They analyzed how this value of NF critical behaves if you try to analyze different channels. This is analog of what in QCD studies is known as search for the maximally attractive channel. And not surprisingly, they found that the more channels you include, of course, that actually raises the value of NF critical to weaker coupling, so it becomes larger if you include more channels. So for me, what's going to be important is not so much the value of NF critical, but what happens there. After all, if we are to trust any of these predictions with an accuracy that all of the studies tell us, we better trust, or they better be correct about qualitative features of what's going on there. And what are the qualitative features? Qualitative features that they predict is that this dependence, same dependence as I showed you before, is actually linear with a number of flavors. And if you look at what the renormalization group flow is doing, at least in those approximations, they find that there is a stable fixed point. This is our QED fixed point, conformal QED. And in the vicinity of it, there is another fixed point, which is unstable at larger number of flavors. It's a version of Gauge-Gross-Neveu model, very similar to what Igor was describing this morning, which come together, go through each other, and exchange their stability properties so that below NF critical, this guy is stable, and conformal QED, see, I'm tempted to talk about QCD. Conformal QED becomes unstable. They exchange their stability in this linear fashion, and that's what's going on. What I described for you here, if I now translate it to the language of dynamical systems, so now let's feed it into the machinery and try to see if we get anything new out of it. And again, this is just the simplest possible bifurcation analysis that I'm going to do for you. What you learn is that this is what's called transcritical bifurcation. This is same kind of bifurcation that I showed you in the very first slide in this model of sheep and rabbits. And it describes precisely this behavior. So this NF plays the role of a parameter of a system. So we're talking about dynamical systems with a control parameter. And question is, what happens to critical points as we vary the dial, as we change the control parameter? You should imagine that there is a flow omitted in this picture because these bifurcation diagrams are supposed to simplify our life, focusing on essential points, namely on critical points of the flow. But you should imagine that there is a flow toward the stable regime here, to the stable point for every value of NF. And unstable point is where flow goes away from. So if I were to put the lines, they would be going to the red line, and from the blue line toward the red line, and downward from the blue line. So I would make a picture very busy if I try to put it over everything, but you can easily reconstruct it by yourself. So this is local model for equations which describe this, and this is the coupling space where this process happens, this bifurcation happens, and this is the parameter, the dial of the RG flow or control parameter of the dynamical system. Now, already here I can make a point that the structure of what can happen and how it can happen and all kinds of topological invariants will grow in a very interesting and highly non-trivial way with two things. A, number of parameters, and B, number of relevant, no pun intended, couplings that can participate in the system that we want to study. So if you have a highly multidimensional RG flow that involves many couplings, it will exhibit very interesting behavior, and even more so if you have several parameters. So that's why QCD, which has number of colors and number of flavors, is actually much more interesting. Now, I promised you something simple, and this is really simple. The point that you learn immediately once you learn about tricritical bifurcations in a textbook on dynamical systems is that it's so-called structurally unstable. In other words, it should not exist in any dynamical system with a single control parameter. And if you think about it, the model of rabbits and sheep that I showed you in the beginning had three control parameters. It was a three-parameter model and a two-dimensional flow. And here, it should never be found simply because either perturbative high loop correction, which would come at 50 loops, or some non-perturbative correction should destabilize this regime. So it could be found in higher dimensional in many systems with many parameters, such as QCD, but not here. Here it has no right to appear in the first place. And conclusion from this analysis is precisely the square root instead of linear dependence that I showed you before. This is something very intuitive, and I can easily try to explain it. What happens is that, again, the system requires fine-tuning. And if you include corrections, and again, unless you have some symmetry protecting your behavior here, this kind of behavior, these corrections, sooner or later, will change this behavior into either this type of behavior where critical points come together and annihilate an emerger and annihilation and then get recreated, or there is another type of behavior which can happen. The algebraic structure that you see here is, in fact, very similar to what we see in resolution and deformation of the conifold geometry in a Calabi-Yau. So math is somewhat similar. And surprisingly, I found that even though these diagrams called unfolding of bifurcations are often used in dynamical systems, these people actually don't have names for these two possible ways of resolve transcritical bifurcation. So I think by unifying the subjects, like Nati proposed yesterday, we have an opportunity to give names to these behaviors in dynamical systems, so we can transmit the names deformation and resolution into their language, and I think they shouldn't object because there is no other candidate so far. This is, they don't have names. This behavior is more common, and I was thinking that this is obviously more likely, and this is kind of boring, where QED would actually exist for all times, and again, this is kind of ruled out by many observations and theoretical studies and so on. And I didn't really take it seriously until very recently. So I think in a slightly different version of QED, so here I'm talking about non-compact QED, which has gauge group R rather than U1, so it doesn't have monopoles. But I think in other versions, this may actually be relevant, and my interest on this was piqued after a recent paper of Nati and his student that Nati mentioned yesterday. I was planning to mention, this is another illustration of why fine-tuning is needed, or why we're talking about structurally unstable bifurcation. So imagine that you know asymptotics by some sort of calculation, by some sort of tools. And you're asked to generically fill in the diagram so that you reconnect these lines. And most likely, you would produce this type of behavior. This would be generic. And trying to have these points collide and sit at the same point would be an extra degree of freedom, an extra tuning that you have to do. So that's precisely this essence of what our friends are calling a structurally unstable or higher codimension effect. So we're in a good situation where if linear behavior takes place, this is a sign of some emergent symmetry that actually protects the fine-tuning, that protects the higher order non-perturbative corrections, destroying this sort of behavior. That's good. We love emergent symmetry, so that would be very nice. Again, in this system, I think it's rather unlikely, but it's possible. And either this type of behavior or alternatively, including higher order terms, would also produce the square root type behavior. So in this picture, which is probably too busy and would probably take a little more time to explain, I want to point out just one important, a little bit maybe technical detail, that if you have such bifurcation or something interesting is happening, it means that some of the terms are vanishing in your expansion. And it is really crucial, it's really important to include next to the leading term in this expansion. So when we're doing our G flows and trying to infer some information, it's actually important to include next to the most leading terms in the expansion for us to trust what's going to happen at the transition point. Again, this I don't intend to explain this diagram in full detail, but the conclusion from this bifurcation analysis would be that we get back to the same characteristic square root behavior, which again, I hope one day will be observed either on a lattice or in experiment. Thank you.
If n is discrete, how are you going to have this square root of n?
Well, that's a good question. There are many systems which try to mimic it, and I don't know if how measurable this effect will be, depending on, I guess, various scales and coefficients in there. But yeah, that's a good question. It may be hard to see in some systems. It may be easier to see in others. Just like we're extrapolating in number of dimensions, of course, sometimes we can have systems which nicely interpolate to non-integer values of n. When I was trying to do this search through condensed matter literature and otherwise, I'm really hoping that integer n's will be sufficient to see it. After all, derivative of this scaling dimension will behave drastically differently for linear regime as opposed to square root. So I'm hoping that perhaps that way we can discern.
In this cubic to AN transition that you showed on one of your first slides, people compute the beta functions to pretty high order. Did they compute to sufficiently high order to see the square root behavior?
Not really. Yeah, so there is something interesting that happens. It's and this is technical point. I'll be glad to discuss now this in private. So sometimes this is perturbative effect, and sometimes it really what happens if we try to compute it perturbatively, we also don't know where our fixed point is. And computing the next term and the next term, because we're doing it perturbatively, basically also shifts the value of the point and doesn't change this type of behavior. So sometimes, and this is important, this is actually requires either all loop analysis or perhaps even non-perturbative corrections. If you do what I mentioned very briefly, this analog of Mach in QCD or multi-channel analysis, then it is some of the terms have been seen generated in the right way to do to produce the square root behavior. So I deem it as somewhat inconclusive at this point. At least theoretically, this is an indication how it can happen. But again, I'm really hoping for lattice or experimental confirmation.
Yeah, if I understand correctly, like the RG diagram you showed at the beginning from Leinert's book, that exhibits this feature of passing through each other because the two fixed points have different symmetry. One has ON symmetry, the other one has this cubic discrete symmetry. So there are basically two generic behaviors. One is when they pass through each other and don't annihilate, and that's when they have different symmetries. And then the QED case where they probably annihilate, because then they have exactly the same symmetry. Basically, the two fixed points can annihilate when they have the same symmetry. I thought that's what you were saying, right?
Yeah, more or less, yes. And on top of it, I guess I want to point out that there are different types of behavior. So one of the tools or benefits of this analysis is that it tells us what can happen and how it can happen. Especially in high-dimensional flows, such as QCD, there is a lot more, which I think has been, again, overlooked by our community.
Yeah, for QED, like you mentioned this quartic operator, that has exactly the same symmetry as the QED Lagrangian. So there are two nearby fixed points with exactly the same symmetry, then they annihilate. That's sort of the accepted picture. If the end critical is something about one, which we don't know.
More questions?
Sergei, I have two questions. One is if the action Simons term in your 3D model, if it is going to change your behavior. And the second question is there any way to check your growth, square root n growth holographically?
The answer to the first question, I don't know about the Chern-Simons term. The role of it, again, I haven't been thinking about it until recently. As for, and similar types of systems. As for holographically, I don't think so. That's precisely the point where I hope combining different tools, this could be complementary to holography because this is precisely about small n. And assumption here is that there is a continuous renormalization and there is very small input, but then again, certain topological or other data which would tell you what happens. But this is completely orthogonal to large n phenomena.
You hinted that there's interesting application of these ideas to QCD. What fixed point are you talking about?
Well, in QCD, for instance, this phenomenon where this analogous question of what happens at the lower end of the conformal window. Again, generically, one would find the same merger of fixed points and similar type of behavior, but because now we're talking about system with two parameters, NF and NC, this is actually NF critical, which depends on number of colors. And as we change number of colors, there would be now interesting phase transitions in this curve as NF critical depends on NC. And in fact, we can find now transcritical bifurcations and more interesting higher codimension phenomena as well. So it's actually interesting, more interesting phase diagram.
10 years ago in a string conference in Madrid, I gave a talk on quantum phase transition, precisely this sort. And that's just precisely modeling the graphene system using ECD7, coordination 6. So that's large NC limit of your system. And this square root n just appears very naturally from just the level proceed, which is just the hallmark of the quantum phase transition. And this was already observed a long time ago by Miransky in this context. So square root of n, nf minus nf critical, that's not new. I mean, that's already well known. And so you have just some simpler way of interpreting it. And again, the square root of n appears from the holographic picture, even though it's not 2E, but large NC, by looking at the D6 brain configuration, looking at the string diagonal fabrication, and the square root of n behavior occurs very naturally.
Yes, I have to comment on the first part. So I totally agree that this is new, and there are many systems where a similar square root has been seen before. In particular, there is beautiful work of well, conformality lost and many other papers where similar behavior happens. That's absolutely true. What I want to point out is that, for instance, very naively, if we think about if we don't really apply this analysis carefully, in QCD, we would conclude that, yes, there is this square root behavior and just annihilation. And we would miss interesting phase diagram and phase structure that as NC changes and have critical dependence on C and what kind of things can happen, they would themselves undergo transitions. So what I'm trying to point out is that this is a new tool, and in some cases, it reproduces known results, and here I agree, it predicts rather generic behavior, which luckily has been seen in other systems. But for example, in QCD, where this actually has been proposed, I think more interesting things happen. So.
Going to the table with the many predictions for n critical. In every one of these calculations, what symmetries manifest in the calculations? And in particular, do you have the full U2 and SU2 and F and time reversal and so forth, or only a subgroup of that is manifest?
Well, I guess in that case, it depends really on calculation. There are so many of them, and they're of completely different flavors. So I put together both theoretical and lattice studies, so I'm not even sure if I should reach that. Yeah, that's what we're talking about. In fact, some of them are theoretical and based, for example, on F theorems or epsilon expansion and so on. So F theorem, of course, assumes all discrete symmetries and full global symmetries. Epsilon expansion is a little bit more delicate because we start with 4 dimensions. On a lattice, most of the time we preserve all of the symmetries or most of them. So it depends, yes. I don't think I have uniform answer to that. Sorry, can we give microphone to Nati, please?
I have a question whether you can really regularize a system in such a way that you preserve all these symmetries. But what you're trying to see is chiral-symmetry breaking in a channel for the symmetry that is easier to preserve in the regularization. This way you might find that the symmetry breaks, but in fact it doesn't.
Yeah, I totally agree with you, and I was quite worried about the same issue when I was going through this, yeah.
Okay, since the time's up, let's thank Professor Gukov again.